of food, okay, or cooking specifically. So we got our daughter one of these a while back because she wanted. Is anybody ever familiar with this cooking technique?
It looks like they're just putting a packet in one.
They are, and that pack actually is vacuumed. It's called, I don't even know how to pronounce it, but we're going to watch a video on it here in a minute. I've heard of this.
So you just
before.
bought her the pack?
We
Just
bought her
boil it.
there's a,
Isn't that how the military does it?
could be.
I don't think they're. Let's do MREs. MREs. They're much grosser.
Well, we bought her like a chamber, and then it's like a stick, and it heats up the water to boiling. That's what it looks like to me. And she can do it like it, so she can cook her food in anything, but you just boil the water. So, I don't know. You're right. It's like, if you just boil the water, what's so high tech about it? But that's a good question. Right. And the thing is, it takes longer to cook this food. Like a pressure cooker, shorter times. Microwave, shorter times. This French sounding technique, longer. But it'll be more uniform. So let's watch this. Feel like you're on watching did you find it?
I'm a doctor. He's a salesman, not a doctor.
He says he's
Adam's looking it up.
Whoa.
How much are they?
Well, none of them look like that one.
Ours looked like a wand thing.
These are just like, wands. They're like
$1.25.
But I don't see, $1.50. Oh, that one, this one's $300.
I'm just putting it out there.
You could buy 1.5 pairs of dark price.
Well, how about this? How many people have a microwave in where they live? No microwave?
Yeah.
Microwave? Microwave?
Yeah.
Okay. Well, so the deal about microwave is, if you remember, like I put it on the board here before, don't do all of them, but we have visible light, and then we have infrared, and then we have microwave. And infrared, so it's visible light, IR. IR is heat. So usually we're using heat to cook our food. And then we have microwaves. And actually, I didn't bring it in but in your textbook, there's your turn, and it says, well, what if we used radio waves? That really hurt my brain. But anyway, using microwaves to cook. And I think I'm going to show you this video. And basically, what those longer wavelengths do is get the molecules rotating. So all matter is in motion. There are different types of motion. Okay. And so it's a special type of motion that energy does to our food. So we're talking rotations of 2.5 million times per second. That's a lot of rotations. There are some limitations, though. Maybe you already know this, but microwaves only go to the first 1 or 1.5 inches of the food, and so the thick items have an issue. That's why you have setting times. You nuke it, you let it set, you nuke it, you let it set. So let's see what this video does.
So are they actually bad for you? I mean,
are microwaves bad for you? That sort of radiation?
Yeah, to cook your food, it seems fine.
But if they were to escape, I don't think that would be good. I mean, I don't know.
I didn't think that they were good for you, though. Like all that radiation waves that's getting produced in your food, if your microwave isn't.
Well, after it warms your food, there's nothing lingering when you take your food out of your microwave. I really.
But like that is going into your food to heat it up.
Right.
It's not really.
You're not. Your food's not irradiated. That's not. It's not like ultraviolet irradiated or anything like that. I don't know. Well, let's see.
I just don't see how it could disappear.
Well, let's see. I could put all those waves up there, and sometimes they sound scary, but dang, we're just. I mean, if you're walking around, you're getting hit by all sorts of different energies. But he did say. So anyway.
They seem to not know if it's that they actually move the molecules faster, or?
Yeah, rotated them, yeah.
Well, he said they weren't sure if it was that or if it was the other.
Got the sugars and the fat, and then they got yeah, it's interesting. What's that?
It shouldn't.
I think it was like any of these modes of cooking, like he said, you are changing at a molecular level what you're eating. So that's kind of what you need to go back to. What else we got? Oh, no heat food preparation. Anybody do any dehydration of stuff?
I had one in first time.
Food dehydrator? Yeah. So if you dry it, you remove the water and it can last longer. Okay, so drying or curing. The curing part means that you actually add salt to your thing you're drying. So you dry it and add salt. I know with regard, I guess I read, with regard to meats, a lot of times we can add nitrates or nitrites, and they will help kill bacteria. When we use salt as a drying application to dry things, we're actually using that process of osmosis, because water is drawn from the cell of the thing you're trying to dry into the salt. So, talk about osmosis, reverse osmosis. Smoking meats. When we smoke meats, we are actually messing with the protein, a protein called collagen, which is connective tissue in animals, and we're gelatinizing it. So we're gelatinizing our protein. Collagen's the protein, and here's the yummy meat to eat. So this, and I'm going to take you out to another video. It's going to make you hungry. Of course, when we smoke our meat, when it's done, it's nice and tender. And you might notice that sometimes it has this pink appearance. And that pink appearance actually is the NO2 in your smoking process has made your meat a more acidic environment, and it turns pink. It's barbecue.
So, like, cooking food really isn't that healthy. It's healthier to not cook it.
Well, like,
To digest it. You're getting
if it's
more
cooked.
I was gonna say you get more nutrients and stuff because every time you cook it, something is getting broken and stuff.
Or did you guys just say the opposite thing? Did you
Nobody
say,
said the same thing.
okay, if you cook it, you can get more nutrients? And
You get more out of
see,
it.
I thought you guys said the opposite thing, and you said that if you cook it, you lose nutrients.
Because like, I just think of like a steak. They say you can eat a raw steak, like cut it off of the animal and eat it. Like that's not bad for you. So I didn't know if cooking it is better than leaving it raw because it's it's not everything that's in the original piece of meat.
Yeah, I hear what you're
There's
saying.
parts getting broke down and turning into something else like that. Smoking it,
Yeah,
the collagen turns completely into it.
yeah, right.
So is
Yeah.
that good or is that bad?
I think probably, and it might come up again when we talk about nutrition for our last chapter, but I don't know. What I started to say is these days probably we're getting what we need to in our diets. If we had less options for food, then we might need to be more careful. I don't know.
How come Jello is spelled with a J?
Jell-O is actually like Kleenex. Like Kleenex is a brand, and so is Jell-O is also a brand. And I think it's really gelatin with a G. But you know what I'm saying? Like if you go to Walmart and buy Jell-O, for like a Walmart brand, it won't be called Jell-O. It'll be called gelatin with a G.
Gelatin is Jello. Jello is gelatin in
That, yeah. This is 7 minutes. We'll see what we think.
Barbecue. And we're derived from barbecue, which to the Taino people of the Caribbean islands meant sacred fire pit. We are definitely on sacred ground today, if we can get in.
The science of barbecue.
I'm here to learn a little bit about the science of barbecue, so I came to a man who knows a little bit about that, Aaron Franklin.
Well, that's debatable. How's it going?
So, what is barbecue?
I think barbecue is something that's cooked over a live fire. So that could encompass grilling, slow offset cooking, cooking in the ground, cooking whole hogs over coals. Any of those kinds of things I call barbecue, but really for me, on a personal level, barbecuing is more of a German Czech Central Texas style. That's like an offset cooking. I experiment all the time. At the end of the day, like, feel trumps any like black and white number or equation that you could possibly have. If something's not tender, it's just not tender. If something's dry, it's just too dry. But the science behind these things, how wood burns, how airflow works, if you start thinking about fluid dynamics inside of a cooker, start thinking about all these other things, then yeah, science has a pretty huge part of it. I think good barbecue is a balance between science and just natural gut instinct.
Cooking is really just thermodynamics and chemistry, just much tastier. Inside the smoker, air molecules are moving around really rapidly thanks to that hot fire. They're vibrating all crazy, and when they smack into the brisket, they transfer that energy to the meat, either contributing to chemical reactions or raising the temperature. Meat browns when it cooks, whether it's directly like a steak or hamburger, or slow like barbecue. The heat breaks proteins down into amino acids, which then react with sugars to create this molecular deliciousness, which happens to be brown. Now, it's not caramelization, it's something called the Maillard reaction.
King of barbecue here in Texas is brisket. It started off with whole animals, and you would just sell what you could and whatever as a method of preservation, you would barbecue stuff on like Sundays.
For us to fully understand the science of barbecue, we need to know a little bit about the hunk of meat that we're cooking. Now, meat in general is muscle, which is primarily protein, fat, some vitamins and minerals, and a whole lot of water. Now, brisket comes from across the chest area of a cow, right here. And since cattle don't have collarbones like us, this muscle has to support more than half their body weight. But that means it's got a lot of three things: hardworking muscle, fat, and connective tissue. It's basically the opposite of filet mignon. But if we apply the right kind of science, those three things can come together like Voltron to make something very tasty.
So at the end of the day, you want it to be tender, juicy, good bark with good fat render.
Now, some of you might not want to hear this, but making good barbecue is like making Jell-O. Now, ribs, brisket, pork shoulder, all of these cuts of meat have tons of connective tissue, and molecular glue that supports all of those muscle fibers. Now, collagen, one of the proteins in connective tissue, can make up a quarter of all the protein in a mammal's body. Now, if you cook them fast, these proteins snap up tight like rubber bands, and they have the texture of them too. But if you cook them slow, then they melt. When collagen is heated slowly and held there for hours, its long protein chains break down and water works its way in. And that collagen turns to gelatin, exactly the same stuff that's in this box. That's what makes good barbecue so tender inside. It's meat Jell-O. Barbecue cuts also have a pretty good amount of fat. Animal fats are made of triglycerides, which have mostly saturated fatty acids. Now, these have much higher melting points than unsaturated fats like, say, vegetable or olive oil that you have in your kitchen, because those straight triglyceride tails are stable and they're packed nice and close. If we heat saturated fats up slowly, we can disrupt those hydrogen bonds and they turn to liquid, which is called a rendering and is delicious. Together, melting collagen to gelatin and liquefying fat make meat oh so tender and delicious. You need no teeth to eat this beef.
What's fun about an oven? There's nothing fun about ovens. You know, did they have ovens back in the early days out of, coming up through Mexico? No, you dug a hole in the ground and you bury a head, on coals. You cook on fire. And that's kind of where I'm coming from, is more on a traditional side of it. Like, I'm not going to use electricity, I'm not going to use gas, no assisted, like, any heat source of any kind. I mean, we have light bulbs, and I don't even like that so much. And it tastes good. And that gets into a whole other thing, too, with how you're using wood. Are you using green wood? Are you using dry wood? Or is it post oak, hickory, mesquite, pecan? Any of these different kinds of woods, they all taste different, they cook different.
Hardwoods that are used in barbecue smoke have lots of cellulose and lignin. Now, when burnt slowly, cellulose caramelizes into sugar molecules that can flavor the meat, and lignin is converted into all kinds of aromatic chemicals that flavor the meat and can even act as chemical preservatives. You just can't have brisket or really any barbecue without that beautiful smoke ring. Now, this is some cool chemistry, or hot chemistry. Meat starts out red because it's full of an oxygen-carrying molecule called myoglobin. Now, iron-containing myoglobin starts out red, but as it heats up, the iron in its heme group oxidizes and it turns this brown color. So why is the ring still red? Well, barbecue smoke contains gases like carbon monoxide and nitric oxide, which is made by the burning wood. And that gas diffuses into the edges of the meat, where it binds the myoglobin in place of oxygen. Now, those nitric oxide myoglobin compounds just so happen to be pink. So the edge stays nice and red, while the interior gets brown like normal.
Kind of the art of working a fire is to control those things and get certain flavors out of a piece of wood. And it's not just heat. It's not just the temperature on a gauge. It's how the smoke is coming out of the smokestack. It's how a piece of wood, if it flames up and then it dies out real quick, it's about a heat curve. How long is it going to last? Are you forcing a piece of wood to do something that it doesn't naturally want to do? You can't really make a piece of meat do what you want it to do. You can only guide it to do what you think you want it to do. So kind of go with that. It's all about trial and error. Don't give up. Keep working on it. And if you really wanted to, you could watch the BBQ with Franklin videos.
Out here we might have beer cans and aprons instead of test tubes and lab coats, but barbecue is science, dog. It's chemistry, physics. The best part is you get to eat your experiments. Stay curious and hungry. I'm gonna get some food. Aaron Franklin and a whole.
That's cool. It's okay to be smart. Series is. All right. Well, kind of leaving cooking for other related topics. We've said that actually working in your kitchen is kind of like working in the lab. In the lab or in science, we have quantitative information. Quantitative just means you have numbers there. And then we have qualitative information. So quantitative and qualitative. So with regard to quantitative stuff in the kitchen, I mean, you have temperatures, you have amounts, numbers associated with those things, melting points. Qualitative things would be maybe more subtle, changes in the textures, changes in the colors, changes in the firmness. So for instance, qualitative, like if you're baking cookies, you just eyeball things, right? So in order to see if your cookie is done, okay, you might put your finger on the cookie to test the firmness, or you might just look at it to see if you got it brown. And maybe you like your cookies chewy or crispy. So those would be qualitative things. This over here, I don't know if you guys have ever made candy, but on a candy thermometer, they'll have these things, like they'll say on a candy thermometer, say thread stage, softball stage, firm stage, hardball stage, soft crack, hard crack stage. And what they're talking about is what is sugar doing? Okay, are you going to be able to take something sugary and will it be a thread sort of thing? Or will it be a hard crack? So as it's listed here, this would be the cooler temperatures down to the hotter temperatures. And it's kind of cool if you've done much with, and I haven't done a whole lot, but with making candy, you'll have something sugary on the stove and it will take forever to get, for instance, to the softball stage. And then right after that, it just shoots up. And it has to do with the chemistry that's going on in your pan. You're cooking, always think of breaking things down. So a lot of new things would be formed too. Right? So one of the things, and actually a lab I have my eye on for us to do yet this semester, we're kind of running out Tuesdays, is sugar content. And you can actually use this thing called a hydrometer. I'm trying to think somewhere, I think I used one of these things before. It floats. So you can kind of see the thing floating in the water, and it's got weight here. It's got empty space here, so it's calibrated to float just right. If you are into making your own alcoholic beverages, sometimes you need to know what your sugar content is, because your sugar in your alcohol is being converted to alcohol. Sorry, your sugar in your fermenting wine is being converted to alcohol. So sugar content is important to know. So the hygrometer will float or sink based upon the density that that bulb is in. So let's see, how would this work? If your solution is more dense, then it will float up high. If your solution is thinner, less sugar, it will sink down farther. So you can kind of see these gradations on here as to sugar content. The value you get back from a floaty thing like this, a hydrometer, is actually called the gravity, or specific gravity. So, I'm not going to show you the video. I wasn't real impressed with that one. What else do we have? Well, again with the sugar, let's see, and I didn't do this, but it makes me want to try. We could go ahead and in the lab get some beakers, put water in it, and then put a little sugar here, more sugar here, more sugar here, more sugar. Keep increasing the sugar content. Stir them all up so it all dissolves. And then what we would see is these different solutions would refract light differently. Like, what do you mean by refract? Well, I mean kind of bend. So if you take a pencil and put it in water, okay, in a glass of water, you kind of look down and it looks like the pencil's kind of disjointed depending upon kind of the angle you're looking. That's refraction. So these would all refract differently. And so that's actually another way that they can get to sugar content. So refraction means to bend light. So light is bent differently by these different sugars. So the two things we looked at, the refractometry gives you a refractive index, and the hydrometer give you a specific gravity. So they both give you sugar content. With regard to specific gravity, well, I guess with regard to both these two, densities will increase, kind of my beakers here, densities will increase from left to right. So what this is doing is just showing you the correlation. I have the word correlate. If two things correlate, that means they go together. Okay, in this case, as the refractive index goes up, the density goes up, and the specific, it's going up, the refractive index is going up because the density is increasing. The specific gravity is also going up because the density is increasing. So they correlate well, not so surprising. Two ways to get at sugar content.
What was the word for hygrometer?
Density, yeah. Sugar content. Carbonated beverages.
Is it supposed to be hydrometer like this? Because there's not a hydrometer and a hydrometer.
Because I might have written it wrong. This hydrometer. Oh yeah. It should be, yeah, see, I'm sorry, yeah, that should be hydrometer. Yeah. The D with a D. Actually, there is a hygrometer, but I wrote that one, and that's right. Hydrometer. Okay. So, a solution. So solutions are when you, solutions are a type of mixture when you have two or more things that are just all the way mixed up, a homogeneous mixture. So we have this, I gotta remember these here. So if we think of soda pop, No matter. Well, I think a soda pop, it's got the fizzes in it, so this is my soda pop, and I'm going to go ahead and put a seal on it. Okay, so these are my CO2 particles. CO2 gas in my bottle, my 2-liter bottle pop. This means it's sealed. Okay, so that's a solution. That's now. Here's the deal. If we open it, what happens to the CO2? It fizzes out. Yeah. Have you ever done this where you can put this is like champagne or it's also carbonated? But if I were to put a raisin there, actually that provides a surface for the CO2 to kind of come out. So
What?
a raisin, like a raisin.
Another
You can do with that champagne. I think you can do it with pop too.
What do you do?
You just like put some, I'll try it at home, but you put a raisin and the CO2 gas particles kind of come there and make the raisin float. Maybe it's only champagne. Yeah, you guys, so you guys said when I open it, the CO2 comes out, and you're right. So here's the deal. Normal normal pop actually has a high pressure of CO2 gas at the factory. That's how they got it to stay in there. And how it stays in there is according to what we call Henry's law. So how a gas, any gas, in this case CO2 gas, stays in a liquid, in this case sugar water, which is our pop, does so according to this relationship. So this is Henry's law. We don't do a whole lot of formulas in this class, but C stands for concentration, and the concentration is in molarity. The K variable here stands for Henry's law constants. Notice that Henry's law constant is very specific. So in this case, we would need a Henry's law constant K that was specific for, bless you, for CO2 gas dissolved in pop and at a certain temperature. So those three criteria: the gas you're dissolving, the liquid you're dissolving it in, and the temperature at which you're dissolving it. So they're pretty picky. The other thing is you need to know the pressure of the gas above the solution. So here when I drew this, I could have, and I'll go back to making it sealed again, I told you there was high pressure CO2. And to me, Henry's law, there's a lot of laws in science. I'm like, well, no duh, right? Because I'm like, if you were to jack up the pressure of the CO2, what do you think is going to happen to the amount of CO2 that goes in solution? It's going to move more. That's it. That's Henry's law. Okay. So the P part also says is if you make the pressure of the gas above your liquid more, it's going to go in the solution more. Your C is going to be more, which is your concentration. That's it. It's pretty straightforward. So thus, the higher the gas pressure above the liquid, the, what do you think goes there? The blank gas will be dissolved. The more, yep, more gas will be dissolved. Exactly. And so I think on the next slide, I have a, dun-dun, your turn. Now we're going to work this problem, and then I think at the end I'm going to tell you why I just don't think this is, I don't like the information that the author's given, but we're going to work it as they say it. And I looked at my desk this time. I checked with the back of the book. So I'll let you kind of read it, soak it in, and then I think we'll go around the room and I'll ask you specific questions. I'll draw some figures here to get us started. So here on the left, I'm going to draw my bottled pop. And so I'm going to show its bottle by putting a cap like that. Here's my liquid. And it gives me some information. Here's my open bottle. Okay. So that one's open. Okay. So Autumn, let's start with you. Can you tell me the temperature at which this is occurring?
25.
It is 25 degrees Celsius. Thank you. So Natalie, can you tell me the volume of liquid? The volume of liquid. Like on the, what number looks like a volume up there? No. What does ml stand for? Milliliters. So that's your volume. Yep, 500 milliliters. Very good. Okay, Billy, can you help me because this will make the problem easier? 500 milliliters, how many liters is that? Half. Thank you. Are we good with that? I'm going to go ahead and put 0.500 liters. Perfect. All right. So, back to you, Taylor. For the one with the lid on it, what is the pressure of the CO2 gas? Very good. 1.25 ATMs. And that's, I'll go ahead and put, that's the pressure of CO2. I put P sub CO2. Awesome. So, I don't know if I want to ask this in follow question or not. I think I'll just state it this way. See the hint down there? What that hint means, and I'm going to go ahead and put some gas particles here. That's my CO2. What that hint says is we're supposed to use 1.00 atmospheres is the pressure of the CO2 over here, which I don't entirely agree with. So I need a question, Glenna. Glenna, what is the Henry's Law constant here?
That's a 0.031.
It is 0.031, and that's moles per liter. And then Henry's Law constant also has in the denominators moles per liter and also units of atmospheres in the denominator. So, Autumn, can you tell me one more time, what is Henry's Law? What's the formula? Yep. Awesome. Okay. So, Natalie, C is equal to KP. So C, help me out, is equal to, tell me what those two numbers are. Marker's bad. What's K? The top of the board.
0.03.
Yep. Ah, much better. Moles per liter atmospheres. And what's P? Yep, thank you. Billy, get your calculator on you? No. What's that? Okay. So while she taps that in, Billy, help me out. What will the units be? Yep, moles per liter. Perfect.
0.039.
Thank you. And that would be moles per liter. Awesome.
So, how do you get 0.5 liters?
Oh, how do we get 0.5 liters? We could have done one of these 500 milliliters. Oh, sorry. Over. You would tell me how many milliliters in 1 liter.
1,000.
Right. If you take 500 divided by 1,000, you get 0.5. Let's see, where were we? Glenna? Did you answer one?
No.
Okay. Let's see. All right. So here, and I haven't even gone there yet, but let's just see what we can do here. Can you, if I have 0.039 moles per liter, I have a half a liter, how am I going to get to moles? I have a half a liter, and I have 0.093 moles per liter. Oops.
You'll have to put liters on top.
Yep.
You cancel out.
Yep.
So divided by liters.
Yep. So if we take 0.039 times 0.5, 0.039 moles per liter times 0.500 liters, that will give us moles. You buy that? Okay, so
Why do
on
you have 0.500 triangle? So that's an L.
then it crossed out here.
Well, culinary rule. Never mind. That's the same thing. Okay, you want me to put that in?
Please.
.0195.
Thank you. And Natalie, what would units be?
Moles.
Just moles. Yep, very good. We're gonna kind of pick up where we left off, but before we, yeah, I'll just snapshot this and we'll finish this on Friday. Okay, starting with Billy. So you better be here.